Hello everyone, welcome back to part 5 of this series. In this part, we are looking into the impact of different types of manufacturing and in-service defects found in composites and their effect on implosion pressure resistance. While expressions such as the equations discussed in previous part can be used to estimate the behavior of ideal cylinders, which are under high external pressure, real cylinders always contain defects. The main defects found in composite tubes are ovalization, porosities, delaminations, and fiber waviness. Any geometrical deviation from cylinder, whether it is out of roundness, which may be caused by creep during cure. Since I work in offshore underwater pipeline design, we as designers have to design against collapse. For a perfectly round pipe, collapse pressure is very high and can be computed using fundamental solid mechanics principles. For example, a perfectly round linear elastic thin-walled pipe subjected to an increasing external pressure, the pipe would remain circular until the pressure reaches the elastic buckling pressure, which is given by this equation here. You can see it's a function of elastic moduli, Poisson's ratio, wall thickness, and outer diameter of the pipeline. This pressure is quite high for many subsea pipes. However, if the pipe has ovality, which could be due to manufacturing, installation, and/or operation loads, this changes and reduces the collapse pressure. For a subsea pipeline subjected to only external pressure, the collapse pressure can be given by this equation here, with this complicated equation as you see, where PC is the collapse pressure, this is the elastic buckling pressure, this is the pressure at yielding, F0 is the initial ovality parameter, which is computed based on the maximum and minimum diameter divided by the outer diameter, and then T is the wall thickness of the pipeline. These equations you can find in many standards or design codes such as DNV and British Standards PD8010. You should appreciate that this complex relationship only considers external pressure, but in reality submersible or pipeline can have a combination of loading. This makes life very difficult to come up with relationships which account for the interaction of different loadings. There are some conservative equations available, but for complex geometries and loading, computational modeling is used as discussed in the previous part. Both porosity and fiber waviness have been shown to be particularly harmful for compressive properties. An estimated loss of 10% compression strength for each percent of porosity has been reported by Soares and colleagues in 1993, while various other researchers have shown the importance of fiber alignment in compression. This figure shows a schematic of the failure mechanisms influenced by a void for the extended model composite under longitudinal compression at different stages as shown in the screen here. The first step, as you can see, is the unloaded condition while you apply a compressive load. In the second case or second diagram, it shows the longitudinal debonding as you see along this here. In the third phase, you see fiber failure. So under compression, they start to buckle and then they start to fail. In the fourth figure, you see the failure of additional fibers and kinks, which is happening in the structure. And finally, the kink bends start to propagate and you will see a final failure. This has been reported in many research papers by researchers, and this one has been reported by Liebig and colleagues from Technical University of Hamburg-Harburg in 2015. The influence of such defects on implosion pressure depends not only on the overall dimensions of the defect but also on its shape and its position within the wall thickness. For example, a delamination near the outer surface may not affect implosion pressure, while the same defect near the internal surfaces can buckle and initiate premature failure, as you see in this video as well. So you see internal delaminations. This makes the prediction of the effect of even geometrically simple defects quite complex. A series of small cylinders were manufactured to investigate these effects. The cylinders were manufactured with artificially implanted film defects at different locations in the wall thickness to simulate delaminations. 4 delamination tests on extracted samples and implosion tests on cylinders were then performed. They reported single delamination defects does not have much of the influence on the implosion pressure. However, multiple delaminations do have significant impact on the implosion pressure. Another type of defect is impact damage. Various researchers have studied the influence of impact damage on the implosion resistance of glass epoxy composite cylinders. Rather few data are available for carbon epoxy composites. As an example, damage in the form of dents is one of the most common cause of pipeline failure. They occur due to the impact of foreign objects and other causes during transportation, installation, and trenching. The severity of the dent is measured by ovality calculated with this equation. Dents with delta less than 0.005 have little or no effect on the collapse pressure. However, if you have a dent with delta equals to 0.1, then collapse pressure may reduce by 50%. So you can see a significant impact is present due to the indentation. So impact can significantly reduce the implosion resistance as shown in this figure. You can see as the impact energy is increased in your structure, the collapse pressure reduces drastically. So finally, real composite cylinders, despite estimations from idealized equations, are prone to implosion due to the presence of defects that compromise their structural integrity. So main defects include ovalization, distortion from perfect cylinder shape, porosity, presence of voids or air pockets in the material, delaminations, irregularities in fiber alignment, etc. Any geometrical deviation from cylinder, such as out of roundness or thickness variation, can initiate buckling locally and potentially leading to implosion. Porosity and fiber waviness are particularly detrimental to compressive properties. A proposed 10% compression strength loss for each percent of porosity has been reported in the literature. The effect of defects on implosion pressure depends on their dimensions, shape, and positions within the cylinder's wall thickness. Delaminations near the inner wall can trigger premature failure, while those near the outer surface might not have impact on implosion resistance. Impact-induced defects can significantly reduce the composite cylinder's implosion resistance. This is also reported. And also changing the composite type from carbon epoxy to glass epoxy also changes the properties and the defects which are associated to that. In general, the presence of defects have a significant influence on implosion resistance, and this definitely informs the design, manufacturing, and materials choice to enhance the safety and reliability of composite cylinders. In the next part, I will show you step by step how to simulate these defects and their effect on implosion pressure for composites in FEA. If this exploration left you intrigued, hit that thumbs up and don't forget to subscribe for more riveting scientific explorations. Thanks for joining me, and remember, science knows no bounds. Until next time, keep questioning and stay